Okay, I think we'll get started. Good morning and good afternoon to everybody. Welcome to Canvas Talk for October 19th, 2020. Today's speaker is Scott Chapman, professor at Dalhousie University in Halifax, Nova Scotia. Scott received his PhD from UBC and is currently working on leave, working at Hertzberg on GearMOS, new instrument that will be on Gemini. So today, Scott will be talking to us about uncovering massive galaxy protoclusters in the early universe with the South Pole Telescope. Take it away, Scott.
Great, thank you, Dennis. So just let me get this sharing and going here. How does that look? Good?
Yep.
Great. So indeed, I'm going to tell you about a project that I've been working on for the last 10 years when I joined the fledgling South Pole Telescope project when point sources were popping up in the survey. And my early interest was seeing if any of these very bright point sources were not gravitationally lensed and might be extremely luminous galaxies or even assemblies of multiple sources that might be the cores of forming clusters of galaxies. And a few years ago, giving you a little prelude here on the title page, we identified in detail one of these structures, which has very clearly borne out to be a very massive protocluster structure at redshift 4.3, about 1.5 billion years after the Big Bang. So this was initially discovered by just measuring the core properties with ALMA, as you can see on the left there. 14 sub-millimeter luminous individual galaxies were found in a very, very small region, about the size of the distance between the Milky Way and Andromeda. And we, to try and figure out what this might end up being, we did a little, some hydrodynamical simulation work using these as initial conditions, working with Arif Babul and his student Doug Renahan. And you can see the results on the right, which was initially just kind of a pretty movie to go along with the paper, but very clearly has some interesting science in it as well. All 14 of these galaxies quickly merge within a few hundred mega years and establish themselves as something that already looks like a very massive, brightest cluster galaxy in a rich cluster today. So this is an SPT collaboration project. There's several grad students working with me on this, namely Riley Hill, George Wang at UBC, and Kaya Rottermund at Dalhousie, who just finished her PhD. So I'm going to give you a brief introduction to galaxy clusters and protoclusters in general, an introduction to the South Pole Telescope survey, and describe how I've carved some of the kind of serendipitously uncovering these kinds of objects into a more well-considered protocluster survey within the SPT project. And then inevitably the one poster child object you discover early on ends up getting studied in incredible detail along the way. So I'll give you a little bit of insight into the properties of this this title slide object, SPT-2349. So detecting and studying rich clusters of galaxies in the relatively recent universe, in the latter half of the universe since the Big Bang, is now relatively straightforward and routine, and is quite a mature area of astrophysics. There are lots of robust methods to detect massive galaxy clusters at redshifts less than around 1.5. The number is always creeping up a little bit. The Sunyaev-Zeldovich effect, scattering of microwave background photons off the hot X-ray gas in in clusters. Looking directly for overdensities on the sky of very red, nominally elliptical galaxies that are the clear denizens of rich clusters. They form very early and have used up all their gas, and you get assemblies of very red galaxies concentrated on the sky. Has been very, very effective. Notably, Ray Carlberg and Mike Gladders pioneered this red sequence approach and applied it to a huge area on the sky to study clusters. And then directly looking in the X-ray at the hot intercluster medium is very effective at characterizing the properties of rich clusters. So the progenitors of these rich clusters, are well traced in simulations. You can go to the n-body simulations and see exactly what the assembly of dark matter is doing as it grows from early conditions and ends up as the most concentrated clusters in the relatively nearby universe. But you lose some of those nice signatures because these early structures aren't virialized, so you can't go after the hot X-ray gas or the Sunyaev-Zoldovich effect readily, because that hot X-ray gas doesn't exist yet, mostly. So looking for the protoclusters, the progenitor clusters in the early universe, has been done by just looking for concentrations of galaxies, as you might expect. See if you can find redshift spikes, as Chuck Steidel did in his early surveys, to find potential protoclusters. So the problem there is that you can find overdensities of galaxies, but how do you ascribe a mass scale to it, or how do you figure out what it will evolve into when you don't have more robust indicators of what a virialized mass will be? So people do make progress in this by connecting it to simulations and looking at the growth of structure. But defining what exactly a protocluster is and what its mass scale is are not totally straightforward. So even if it's not completely obvious what a protocluster is, detecting these overdensities can be accomplished. I alluded to this Lyman break approach. So the Lyman break photometric technique is a relatively blunt instrument because it detects galaxies over quite a large redshift range still, but it does target galaxies in a specific redshift range. The initial Steidel protoclusters from way back in 1999, if that's way back, really only found overdensities that made sense statistically by in the redshift surveys. At redshift 3, they found very strong spikes in the redshift distribution. But now that we can survey vast areas of the sky, like the Subaru Hyper Supreme Cam surveys, you can actually find the overdensities more statistically, even in the photometric catalogs like the Toshikawa protocluster searches. Another technique people have used is to search around relatively rare objects that are thought to trace very massive halos, like classical radio galaxies, 3C radio galaxies and such, and quasars. And certainly the radio galaxy, looking around radio galaxies for overdensities of galaxies have proved to be quite successful in identifying early structures, overdense structures. And then more recently, people have started to ask if these sub-millimeter luminous galaxies that I've spent a lot of my career studying might also be interesting tracers of early structures. If you have these rapid collapse of the cores in the early universe, you might expect a lot of sub-millimeter luminous galaxies. So that's kind of what I'm focusing on here with the South Pole Telescope survey. Just in brief, the sub-millimeter luminous phase is thought to be a phase where you're rapidly forming stars, shown in this simulation from Narayanan in 2009. you can reproduce the submillimeter population with a rapid burst of star formation, or 850 micron submillimeter flux density. So you are forming stars for a very brief period, using up a lot of the gas, potentially lots of feedback, regulating this process and shutting it down relatively quickly, but also feeding active galactic nuclei. So it's expected to turn into an AGN phase shortly thereafter and regulate this crazy process. So quasars and submillimeter galaxies may be connected. But it's thought because it forms a lot of stars quite quickly, it's has potentially nice roles in galaxy evolution, like forming massive elliptical galaxies. So an important phase in massive galaxy evolution. Over the last 10 years, we've started to see these submillimeter galaxies highlighting overdense regions and started to wonder how important they might be for looking at early massive clusters of galaxies. So ultraluminous galaxies is another way to characterize these submillimeter galaxies. I just borrowed this nice slide of Caitlin Casey, who is a former PhD student of mine. Kind of shows this protocluster phase as opposed to the virialized cluster stage later on. And you can see at very early phases, at redshift 6, just a billion years after the Big Bang, you maybe have your luminous burst only in the very core, maybe by redshift 3, where you're still actively forming the cluster, but now there's more action in the outskirts and more massive ellipticals quickly building through more submillimeter bursts, these yellow stars. And by redshift 1, you now have an intracluster medium, which is dominant, the purple. Most of the core galaxies are red, and maybe you still have a few submillimeter galaxies out in the outskirts, as people have found. The last vestiges of infalling rapid star formation. So you could ask if these objects at higher redshifts preferentially live in overdensities. Another aspect of these protoclusters is that they are immense on the sky, as you might expect. There's an awful lot of material that has to collapse down, a factor of 100 or so from redshift 2 down to what you see in the virialized cluster today. Yet the contrast on the sky of all that material will likely be progressively lower and lower. It's hard to probe all of that outlying material because it's less and less overdense compared to the background and foreground galaxies. So the cores of these protocluster structures are what tend to stand out because they're the most overdense. And here's a real life example following up one of the Chuck Steidel protoclusters with first the Hyper Supreme Cam. This is Yuichi Matsuda's and his students' work in a Lyman alpha image of the square degree field around the very dense core. You can see there just several arc minutes across, or 10 arc minutes across. And a student of mine, Kevin Lakai, for his master's thesis, mapped a lot of this structure out with Scuba 2 and found that indeed the most overdense regions, and certainly the core, were overdense in submillimeter galaxies. But the core overdense region in protoclusters is clearly an important and interesting place to study these structures, where you have had the largest amount of collapse and formation happen. And also the fact that they stand out as such high density contrasts means that finding them as early signposts to protoclusters is perhaps more straightforward. And simulations like these ones of Chang et al. Have demonstrated that the cores can actually be quite dominant at the very early epochs from the early collapse of these structures compared to the surroundings. So I just wanted to emphasize before pushing into my survey here that the field of protoclusters as such is still in a state of relative immaturity. Just data collecting and trying to build catalogs and compare different techniques. But there's not a large number of these objects discovered, and especially at early epochs beyond redshift 4. And almost everything you see in this this summary paper of Overzier from a year ago is selected in the optical. And the survey I'm talking about today suggests that many of these most luminous cores, massive cores in the early universe beyond redshift 4 are effectively invisible in the optical, impossible to find from their overdensity of Lyman break galaxies, mainly we think because of dust obscuration. But identifying the populations of galaxies are potentially very interesting, and we'll put it more on an astrophysical framework. This is our work that's already starting. You expect these protoclusters to contain galaxies that are older and more massive compared to field objects. They've likely experienced more major mergers compared to similar galaxies in the field. And this merging activity stimulates the AGN and star formation activity, and of course determines the morphological kinematic properties of the galaxies. So you might expect environmental differences should be detectable in protocluster cores. So that's another thing we're looking at. So a brief overview to the sub-SPT survey. The South Pole Telescope is primarily a cosmology and galaxy cluster experiment. The first survey covered 2,500 square degrees, 3 wavelengths, 3, 2, and 1.4 millimeters, ideal frequencies or wavelengths to probe both search for Sunyaev-Zeldovich effect in clusters and also to probe the primary CMB directly. Both of these have been key objectives of this. Clusters then show up effectively as shadows, dips in the microwave background. You can see these black dots here, and they're not much bigger than the 0.1 arc-minute point spread function of the telescope at these frequencies. And they indeed have been very successful in a blind cluster survey in this relatively nice technique, somewhat redshift independent technique for finding clusters. And you can see in the black crosses here are all the clusters that this survey found. There's an ongoing survey called 3G, which is expected to push down another factor of 5 in sensitivity and presumably detect these things out to redshift 2 and beyond. CMB stage 4 would push this another order of magnitude in number of detected clusters and sensitivity over the sky. So an interesting aspect of this survey was that these emissive thermal dusty point sources were found, as well as the shadows rising through these millimeter wavelengths. And ELMA follow-up of these sources mostly showed that they were clear, strong galaxy-galaxy gravitational lenses, partial or complete Einstein rings. You see beautifully in the ELMA data. And these ended up being very luminous, dusty galaxies already, and then lensed by another factor of 5 to 10. So that explains why they're such bright point sources, but about 10% of them weren't obvious gravitational lenses, which piqued my interest. So we asked the question, what if instead of a single gravitational lens, this SPT source consisted of many unlensed galaxies at these huge flux densities that the SPT was sensitive to? 25 millijanskis translates to an integrated star formation rate of over 10,000 solar masses per year. So that's a lot of star formation in a relatively small area. There's nominally 1 arc-minute beam of the SPT. So these would be extremely active protocluster cores, and in the early universe, as they were being identified spectroscopically in the redshift 4 and out to 7 regime. So before we launch into what these things look like, well, why do we want to study protoclusters? It's relatively obvious that you want to see what the progenitors of rich clusters look like. But in principle, you could try to do some of the interesting things you currently do with rich galaxy clusters. So they're much like rich clusters themselves, but at much more formative stages. In principle, you might be able to use them as cosmological probes to probe the growth of fluctuations in the very early universe directly. You could get a handle on your selection functions and things, but you can probe the dark matter substructure within them. the formation of their brightest cluster galaxies and other populations, the AGN feedback that regulates the galaxy growth, what's happening at the critical point here in the red sequence evolution when they're effectively doing all the star formation that leads later to the red and dead massive galaxies, the environmental effects that we highlighted on, the actual enrichment of the intra-cluster medium, and the triggering of the supermassive black holes in these dense environments. So there's lots of great reasons you want to characterize a sample of protoclusters, not just find them haphazardly, but actually go about it systematically. So just as a reminder, this one poster child object from the front page, title page, it has some very interesting properties that separate it from the typical gravitational lens we saw as the typical South Pole Telescope thermal dusty source. So it resolves on scales of about an arc minute and a half into a series of bright objects within an instrument like Scuba 2 or Apex Leboca in the south, which has about a 19 arc second beam compared to the 1 arc minute beam of SPT. And you can just see that compared here. The SPT contours are clearly extended north-south, even though the beam is comparable to the size of the source. And that's clearly driven by these multiple sources resolved by Apex with a 20 arc second beam. So it's extended on the sky beyond the SPT beam. So that's one clear signature to look for. And then the key is resolving it with ALMA, finding that indeed even that one central bright source is composed of many individually luminous galaxies, and even resolving them spectrally to get the individual properties of those galaxies. So this is just an example of what this looks like in the real SPT data. This is a little bit of a cheat because it's the next generation SPT pole survey, which is much deeper than the original SC survey that we found these things in. So this poster child source is now detected at about 12 sigma. And you can see the zoom in here and the resolving of that source like we showed before. But it clearly stands out like a sore thumb in the SPT data. It's the only point source easily within the 4 square degrees anyway that shows any spatial extent with the SPT beam that's significant. These crazy looking rings are just filtering artifacts. They're not real structure in the map. And then just compared to what Herschel sees. So this is these regions have all been mapped with Herschel Spire, fortunately. And you can see that the source now, it stands out, but not because it's brighter, but only because it's a bit redder because of its redshift. So indeed, these things can be found within the Herschel survey, but they don't, it's still a bit of a needle in a haystack issue for the Herschel surveys. There are other red things all over the place with in much smaller areas with Herschel that aren't protoclusters. They're just red sources. So here's my go at an initial sample. I found all the things that at some level were spatially extended in the SPT and their single dish follow-up at 850 microns with Leboca. And a lot of detailed work as either photometric redshift or spectroscopic now for almost all of these has shown that they lie between redshifts of about 3 and 7. And this is the 870 micron contours on top of the Spire images, Herschel Spire images, and they're 9 random places within the SPT survey amongst about 10% of all the emissive point, dusty thermal point sources. So let's refine this a little bit. This poster object 2349 is the most spectacular object of its kind, clearly. But it depends how you define most spectacular, because some of these things are extending out to redshift 7, where the conditions are much different and much more challenging to reproduce in simulations. But as we said, knowing what to look for, can we find other similar systems? It's a summary sample selection paper I'm trying to finish up here. We already talked about the Leboka structure in the center resolving into multiple sources. Here's 7 of them showing that they very clearly do resolve with ALMA into handfuls of sources. In the deep follow-up with Gemini and Spitzer IRAC, we don't find any plausible lens galaxy or even a cluster or group lens that might be doing gravitationally lensing this object. So it's clearly an assembly of unlensed sources. And then also recently, deep single dish 850 micron Leboka follow-up shows that there's all of them have overdensities of very red satellite galaxies in the much larger surrounding field. I can just show you that quickly. This is work by a master's student of mine at UBC, George Wang. So this is about a 160-hour program with Leboka on Apex, and deep near confusion limited maps of each of these fields. And they all show strong overdensities just purely by surface density here. This is including the bright central objects. This is the SPT counts compared to the field counts. So as you go brighter and brighter, you're getting up to orders of magnitude above the field, but even down around bright but not super crazy objects, you're an order of magnitude overdense. And following up with ALMA, these satellites, they don't all immediately jump out as protocluster members, but some of them are going to be field contaminants anyway, and limited bandwidth means we can miss some. But we're clearly finding some of these red satellite galaxies are at the same redshift with ALMA. So this is work in progress as well. So let's go back to our title slide poster object and look at it in a little more detail. It was initially announced as a kind of protocluster candidate in 2018 with a student of mine, Tim Miller. And then a student, Riley Hill, has been studying this in more detail and over wider fields, and indeed has now found 33 submillimeter luminous galaxies in the extended field, many more in the core region. The pink points are the new ones. So there's about 26 within 150 kiloparsecs there. And then there's 2 clumps of objects further out at clearly 2 different redshifts that don't look even remotely bound to the central object, but are clearly close enough in velocity that they're going to end up in the same structure. So there's this northern clump and then a northwest clump over here. So this is the overall redshift distribution of all 33 of those objects. So there's mounting evidence that there's not just some kind of a core collapsing object, but there's a real protocluster over the extended region here. So the key results coming out of all of this, not just for this object, but all the objects, are that these are clearly candidate protocluster cores in the early universe at an advanced stage of collapse. And they're the most concentrated and highest star formation rate systems we know of. They're all in this 10 to 1700, 17,000 solar mass per year range. And their cores are just incredibly overdense with a million solar mass per year per megaparsec cubed in a central kind of arc-minute scale. And then, so that's the star formation rate versus area. So here's the example of the 2349 object compared to any other protoclusters that have been studied, and also compared to any kind of simulations. So they elude, they are unexpected in some sense, as many of these kind of crazy objects are. So it's the most massive halo we know about kinematically as well. It looks like it has a virialized core of about 10 to the 13 solar masses. And if we look at what we expect for the Coma cluster here, up above 10 to the 15 solar masses at redshift around 0 epoch, its gray envelope is what you expect the progenitor of the core region to have evolved like. And here's our 2349 object, which within considerable uncertainties in what its mass scale are clearly a good candidate for the progenitor of something like this Coma cluster. These are all clusters that have been well characterized either through their X-ray gas or through the Sunyaev-Zeldovich effect. the SPT points. So that's all fine at redshift 4. There's tension there. The issue that we see immediately is that at higher redshifts, redshifts 5 to 7, this tension gets much greater. So here's again star formation rate on the y-axis versus area on the sky. So the concentration of the star formation. And these redshift 5 to 7 objects are way up in a similar range to the 2349 object at redshift 4. But now, instead of the redshift 4.5 model, we need to look at a redshift 5.5 or higher model. And now you just never see these kinds of things collapsed in the simulations. So one issue here, of course, that the simulators love to point out is that they can't probe anywhere near the volumes we're probing with our big SPT survey. So they have kind of gigaparsec cubed simulations. So they might say, well, it's not our star formation recipes that are wrong for finding these things. It's the fact that your thing is so rare, we don't see it in our simulation. And that's a fair point. But if you look at the trends, the amount of star formation per halo that they're finding in these collapsed regions in the simulation are nowhere near enough that they would scale to anything like we see. So even if you found an object with a few more massive galaxies within the relevant region, it doesn't seem like the simulations would easily produce the types of things we're finding. So the most obvious thing is that the star formation prescriptions are not adequate to explain these kinds of objects. Even though these SPT protoclusters are very rare, they are, even if you look at empirical models, they're still way more than you predict. So this is the redshift greater than 4 counts of protocluster objects in simulations that people have looked at. And you can see that the prediction in these red curves, in the paper, they were happy that they reproduced the one known thing at redshift 4 quite well, but our 10 objects are easily in order of magnitude or 2 above any kind of extrapolation of the model. So they're unexpected in number density as well. So let's look a little bit at the individual galaxy properties. Recall that we had hoped that you would see some interesting properties of the galaxies in these protocluster cores that would differentiate them from the field because they formed in these crazy environments and inevitably had an accelerated environment compared to the field as well. But even in less extreme objects, in optically selected protoclusters, finding clear evidence for differences between the protocluster and field galaxies hasn't really jumped out as a dominant result. So Kaya Rotterman did part of her PhD thesis looking at this 2349 protocluster. And she's mainly looking at the multi-wavelength optical through infrared, near-infrared properties of the galaxies in the core. And for this, we used GMOS and Flamingos 2 to get GRI, K imaging, and IRAC bands as well. So you can see the ALMA contours superposed on these galaxies. They're mostly undetected in most of the optical bands and then start to pop out quite as mostly faint things in the IRAC bands. But there's enough signal there and enough information over these 6 bands that you can do reasonable SED fitting and get some information. The dominant effect on the spectral energy distribution fitting is the stellar mass. So that's something that's characterized here against the green band is the field galaxies to the extent that they're characterized at redshift 4. So you can see that there's quite a scatter here in our blue points, and some of them are just limits because they're undetected in almost every band. In every band, they're undetected to have these limits put on them. But many of them sit right where you expect redshift 4 galaxies to sit in their star formation versus stellar mass. There's a few tantalizing objects here which are very massive in stars compared to their what appear to be low star formation rates. Nominally, you'd call something like that a quenched galaxy. And environmental quenching is important, of course, but so maybe these things did form a lot of stars and then were quenched as they went through this washing machine in the center of the galaxy. And not many candidates for sitting way above the normal star formation rate stellar mass envelope here. The purple points are other submillimeter galaxies at comparable redshifts that have been characterized. You can see error bars are immense. It's hard to characterize the stellar mass, especially with any reliability, but I think there's some information in this cloud of points. So the punchline is that the individual galaxies aren't particularly unusual relative to the field at redshift 4. You don't jump out, oh, these all formed in this protocluster and they're all quenched, or they're all have star formation rates way above their stellar mass. They're just, it's a big scatter, but they center on the distribution. Kaya also looked for Lyman break galaxies in the extended field with the GMOS data, and started to follow it up spectroscopically as well, with limited success so far. But the wider field does show some Lyman break galaxy overdensity out to about 2 arc minutes radius we can probe around the central structure. The squares are Lyman break galaxies selected in different magnitude ranges, basically. So each set of squares is kind of independent assessment of the density, or you can lump them all together. But in I less than about 26, there's clearly a central concentration of Lyman break galaxies, which falls off to something that's maybe modestly overdense compared to the field estimate at redshift 4, which is this band here. So the takeaway from this seemed to be that it would be relatively hard to find this structure only in the optical from taking a giant hyper supreme cam survey and looking for an overdensity of Lyman break galaxies. It's certainly not the strongest Lyman break galaxy overdensity by a long shot in these big hyper supreme cam surveys. It would be a modest detection of an overdensity by their criterion. We also looked for galaxies in this extended region around the structure with VLT Muse. This is a student in Chile, Jordanka Apostolovsky, and she found certainly a modest overdensity again of Lyman alpha emitters in the surrounding region. These are these red symbols. Interestingly, she also found this big extended Lyman alpha halo, the white contours here, characteristic of the kinds of things that have been found in other protocluster regions. It's never exactly clear what's ionizing these Lyman alpha photons. Maybe a bit of a giveaway is that this thing is clearly quite offset from the center of mass of our system. So it's not obviously probing the dense central potential of this structure. That might just be because the gas, that's not where the gas is, and there's gas out here around these other things which are ionizing it in a much less tumultuous area of the core. But it also could be blue shifted shell ejected, or maybe even a hole in a very dusty structure where the UV photons are escaping. But there's clearly, whenever you look in another way, there's something new and interesting found in this structure. A final thing that Kaya did in her thesis was do a kind of mass budget of the core galaxies, the brightest core galaxies. So she measured, measured the stellar mass already, which is their blue points here. This is just identifying them on the x-axis and their mass on the vertical. And then the gas mass was measured in other papers through CO lines. And then the dynamical mass she looked at in 2 ways, both from the rotation curves of the galaxies, if it existed, or in the dispersion, integrated dispersion field above here. So this is mass versus a dynamical mass estimate versus star formation rate. And they're sort of in agreement, reasonably in agreement. And those are the purple symbols here. So you can see the amount of mass in gas here is green, the amount of mass in stars, which is nominally a bit more, probably not within uncertainties. It's indistinguishable from the amount of gas. The dynamical mass sits above that, which is good. And then the virial mass of the core up around 10 to the 13. So about there's about 60% of missing mass, which is in the halo, which isn't contained obviously in the individual galaxies, which is what you might expect. We're just looking at the cores of the 14 brightest galaxies in this structure. So that all kind of hangs together in an interesting and reasonable way. Oops. So another interesting thing that Riley Hill has looked at a little bit in this 2020 paper is the luminosity functions in these different tracers, the CO and the C+ emission lines. So you can see the C+ lines here marching down from the brightest, where the line is incredibly broad and not a huge. It has a small equivalent width is what I'm trying to say. The continuum is strong compared to the line. As you get down to the fainter lines, they're narrower and narrower, and the continuum is undetectable at the faintest lines, which is kind of interesting. So the fainter sources are more easily detected in their C+ lines than their continuum. But what this looks like in a luminosity function is the blue. So there's a turning point and a clear break point as well, which is nice. But you can see the turnover halfway through where the slope changes between the continuum. So the continuum luminosity function is purple. So it's shallower before and turns over earlier. So you can see a difference in the galaxy properties between the brighter and the fainter ones in that sense. So we've characterized this, but haven't done a lot of the obvious things you might look for in the properties of the luminosity function yet. And part of this is the fact that we have nothing to compare to. So there is no field luminosity function to compare to at redshift 4.5 in the C+ line, which is interesting. It's a very hard thing to characterize, even with huge amounts of dedicated ALMA time. There's no satisfactory luminosity function measured at redshift 4 in C+. So it highlights a prelude, if you want, that you get into this kind of information in these very overdense systems. You can actually relatively quickly measure and characterize the luminosity functions of the galaxies very well in these dense environments. So back to the formation of the brightest cluster galaxy. Well, this simulation really said that, sure, there's a whole bunch of galaxies we're seeing in the core right now. We now see 26, not just these original 14. But they are going to turn into one galaxy very quickly, just a few 100 million years, and kaboom, probably the biggest mega merger ever in the universe has turned into one brightest cluster galaxy. So that's kind of shown here, the mass of the protocluster, the mass of the brightest cluster galaxy in stars compared to the mass of the cluster in some sense. And I'm comparing to sort of redshift 1-ish samples of galaxies, which have some relatively nice relation. And our object is redshift 4 all the way up here at above 10 to the 12 solar masses. It grows by another factor of 2 through this merger of all the galaxies. And even if there was no other growth in the brightest cluster galaxy all the way to redshift 1, it would still be one of the most extreme objects in all sky surveys at some level, field surveys of clusters. So it's interesting. Maybe it's destined to be the brightest cluster galaxy of the most massive cluster in the universe. It's clearly very rare and different from the field clusters, if you can call that. Another little interesting thing, not only are there individual galaxies, but there's this kind of halo of C+ gas we found as well, with some velocity gradient around it, most of it not associated with any individual galaxies. So it's not clear what this is. It kind of looks like a tidal streamer coming off the core, but it could be ejected material or something. So a student of Axel Weiss's in Bonn is working on trying to interpret this a little better. And finally, I just wanted to point out we have lots of other great data, HST data, and both high and low resolution C+ that gives us morphological information. And Riley Hill is kind of working this up for his final thesis paper at UBC. But clearly lots of kinematic information even in the lower resolution data, but certainly in the higher resolution data. Another interesting thing, what about AGN in these galaxies? You might have wondered why I didn't mention AGN earlier, and that's because we effectively don't have any indicators of AGN. They don't come easily in the millimeter. I'm sure some of the objects are extreme broad lines, etc., but they're not. When you look at the properties, it's a big extended galaxy with a big, huge rotation curve. There's nothing about the broad lines that scream out AGN. We did realize, found kind of serendipitously that we'd accidentally tuned to the CO 16 to 15 line and these other OH lines that are messed up with it, or blended with it a bit. So Rebecca Canning, who's a professor now in Portsmouth, has been working on this because of her interest in AGN and the X-ray side of this. So we've been trying to study this object with XMM and Chandra, but in the short term, she's been looking at these very high excitation CO lines, 16 to 15, and asking if they are more like AGN or more like star-forming galaxies locally. And the answer is a mix, I think, but hopefully we'll get some insight into maybe some AGN activity that's required to give some of these excitation curves in CO. And then finally, I touched on the importance of protoclusters for maybe understanding the early heating and enrichment of the intercluster medium. And Arif Babul and Doug Renahan have also been kind of considering that in the simulations and heating of the gas. So even just the gas that we see in these galaxies in the simulation, a substantial part of that gets heated to X-ray temperatures, which is interesting. It's clearly not the dominant heating compared to gravitational collapse that's going to heat up the gas in these clusters, but there's no question, and there's going to be way more gas than we just see in our ALMA resolved galaxies. So it's clear that there's some heating to X-ray temperatures of gas that's going to go on in this violent event from the feedback from all of the star formation and possibly AGN in these individual galaxies. Okay, so I'm getting into my summary here. We haven't gotten too far in flushing out the sample, but we kind of know what the mass scale is of all of them to some extent. And here's that progenitor of the coma cluster plot again, in the tracks of an expected coma cluster. And there's the 2349 object, and here are the other ones. So they're all certainly possible progenitors of a coma class cluster by that metric at least, and some of them seem to be way above what you would expect. And they've collapsed even earlier than the simulations would expect or require for coma. That doesn't mean they have a track that leads to some 10 to the 17 cluster, of course. It just means that the evolution is probably a bit different. We don't see things grotesquely more massive than coma. But there's no question that they're hard to find in simulation. So this is the same plot again, mass versus redshift, but now we plotted the kind of the maximum number of halos that can support a structure of this mass as a function of area on the sky. So this is 25 square degrees. So if you only had a survey of 25 square degrees, you'd be quickly running out of halos that could support this kind of a mass scale. The blue is the SPT 2500 square degree survey. So now maybe we're a comfortable number of halos in the simulation that can support that kind of mass scale. And the whole sky, 4200 square degrees, is a bit above that too. But they're very rare objects that are pushing against the available massive halos that have formed to be able to sustain these kinds of events. And then there's a deeper survey called 3G I alluded to, which is going much deeper in 1,000 square degrees. And we're starting to explore and define how we would go about a protocluster survey in this. I don't need to go into detail, but it's clearly going to require a lot of follow-up, probably more selective follow-up with single dish and ALMA. And I've had students do a bit of forecasting in the simulations with this, and a clear thing that came out of the simulations was that when you get down to these fainter sources in the deeper survey, you're going to find a lot more line of sight projections. So you'll find protoclustery things, but they'll be diluted by a lot more by other objects. So the summary here, I think the discovery of these protoclusters at a very high redshift is only possible because of the synergy between the very large area single dish surveys and the sensitive interferometric follow-up, a lesson that's always been quite important and keeps coming to the forefront as we try and argue for other single dish telescopes to support ALMA. The SPT protoclusters are clearly unique systems to study early phases of massive galaxy cluster formation, even out to redshift 7. Seems clear that brightest cluster galaxies are forming earlier in these kinds of objects, at least, than expected from simulations or observational wisdom. These systems will give us the laboratories to study the galaxy properties in these intense cores and compare them to the field as we look in more detail. So thank you very much for your attention, and happy to answer any questions.
Thank you, Scott. Very fascinating and a very comprehensive talk. If you have questions, you can raise your hand or type them in the chat window. And William Wall, please go ahead with your question.
Yeah, hello. You said that the star formation prescriptions were insufficient to explain what you were observing, the number of objects you were observing. Would you care to speculate on what they're missing?
Well, that's a good question. I should have, we had Douglas Scott and had a postdoc at UBC who recently submitted a paper on this, and I admit I haven't looked all that carefully. I don't know if they came into any obvious conclusions about what it was, but I mean, in a nutshell, you clearly don't have enough star formation per unit mass in these systems. So what that exactly means hydrodynamically is I guess the usual range of issues of just concentrating enough gas and triggering it all to form stars at the same time. So that can be done in isolated cases by the Narianian simulation that successfully produced the brightest submillimeter galaxy known at the time, took two incredibly gas-rich disks and slammed them together at the best possible geometric configuration of the merger, with them counter-rotating and everything optimal to get the gas forming stars, and that was able to do it. But that clearly just that's very specialized situation that doesn't happen in the simulation by chance enough to get these kinds of systems. So I guess it's not totally obvious what the answer is, especially when you're selecting very rare objects like we are here. If they do exist, they will happen. And if the only way to make that happen is very specialized conditions, maybe that could be the answer, but it could just be that the scaling that is being used for star formation isn't quite correct in these environments. But I'd encourage you to ask Segwan Lim at UBC. He's looked at this in detail in the simulations.
Any other questions? So I have a question. What will CCAT be, assuming it gets built, be able to contribute to this area of research?
Well, CCAT will be, I mean, CCAT's power is the high frequencies, so the 350 micron, very sensitive and wide field 350 micron measurements. And I mean, just the direct connection here is that you very quickly be able to isolate samples of very high redshift submillimeter, luminous submillimeter sources with CCAT. So you might be able to sort of short circuit this process that of finding objects at millimeter wavelengths and sifting through them to find the few objects like this. CCAT will do other great things with just detailed characterizations of the 350 micron population in general, which is at the peak of the output of galaxies over a huge range of redshifts. But I think, yeah, the selection of high redshift, very high redshift submillimeter sources will be a great triumph of CCAT prime.
Great. Okay, any other questions for Scott? Doesn't look like it. So thank you again, Scott. Thank you for taking the time to present this Canvas talk, and thanks everybody for attending. And I don't have anybody lined up for next week yet, but if you want to volunteer to give a talk or have a student, let me know. Thanks again. Bye, everyone.